Hey there, this is Reuven Lerner. Welcome to my talk here for PyCon Israel 2021, Avoiding Memory Leaks with weakref. So let's start with something really simple. What does this code do? X equals 5. Now, anyone who's been programming Python for any amount of time has a basic sense of what's going on, but let's think about it in greater depth. Really, we're doing two things. First of all, we're creating a new object of type int with a value 5. And yes, I know that typically Python already has the int 5 established. We're not really creating it, but let's ignore that for now. Anyway, once we have this int 5 object, we are then creating a reference from the variable x to that object, to that integer, as depicted here in a screenshot from the pythontutor.com website. Now notice, Python does not have this idea that we have in some other languages, such as in C, where a variable is an alias to a location in memory. That's not how it works. Variables are names that refer to objects. So let's take a slightly more complex example here. What happens when I say x equals 5 and then y equals x? Well, let's take it one step at a time. First, we're creating that object of type int with a value 5. Then we're creating that reference from the variable x to 5. That's what we did before. But what happens when we say y equals x? Well, first we have to determine what x refers to, and that, of course, is our int 5. And then we create a reference from the variable y to that integer. It is not a reference from y to x, it's a reference from y to the int, as shown here in the capture from Python Tutor. X and y are both references to 5. There is no such thing as a pointer from one variable to another in Python. That idea just does not exist. Rather, when we do assignment, Python always looks at the right side and then the left side. And on the right side, if we have a variable, then it evaluates that variable and finds out what object it's referring to. And then it assigns that variable reference to the variable on the left side. So this is all nice and everything, but wait a second here. Where is Python getting this memory to create this int object or all objects in Python? And the answer is that Python does that on our behalf. We don't need to worry about allocating memory, and we don't have to worry about deallocating memory either. We don't have to worry about freeing it up. And that's because Python is a garbage collected language. What it's doing is something known as reference counting. Each of these references, each of these arrows pointing toward some data is one reference. And when the reference count of an object drops to 0, Python removes the object from its memory and frees it up, returns it to the operating system. Now, this is not the only part of garbage collection in Python. There's both the reference counting and then an actual system they call garbage collection, but we're going to ignore that second part for the purposes of this talk. So let's take some more complex code here. If I have a class person that really does nothing, it's just def under init, self-name, self.name equals name. How can I keep track of how many references there are to an instance of person? Well, I can use that with the GC module. GC4, garbage collection, comes with Python in the standard library. So if I create this class person, and then I create P1, which is a reference to an instance of person, then what I can do is say, hey, Python, show me what is referring to P1. How many arrows are actually referring to it? And so gc.getRefers will return a list of objects. And what does that list look like? Well, when I run the program that I just showed you, I get this. I get a list with one element in it, and that element is a dictionary. And at the end of that dictionary, we see P1, main, person, object, blah, blah, blah. Where is this dictionary coming from? What is this? Well, this is actually our global variable scope. This is the dictionary containing all of our global variables, and we can get that if we run the globals function. That's a built-in function that's always available. So P1 is a global variable. That means it's a key in the globals dictionary. And that means that we have access to it as a global variable. But that also means that if you define a global variable in Python, every time you define a global variable in Python, there is a reference to that variable from the globals dictionary, which means that so long as the Python program is still running, there will be at least one reference to your variable and thus to your data, which means that global variables never go away. And if you have an element of something that's in a global container, like if you have a global list, then elements of that list don't go away either. Okay, well, we can find out, assuming that a variable or that an object is released, is deleted, we can find out when that happens with the dunder-del magic method. And this method is invoked just before an object is about to be released, when it's going through garbage collection. Now, I should note, this is not a destructor method. It's sort of kind of a destructor. It's the closest that Python has, but it's not something you should normally use. There are lots and lots of warnings about when and how you should use dunder-del, so consider yourself warned. So let's look at how we can integrate dunder-del into our person object. So I'm going to add it here, def dunder-del self, and all I'm going to say here is I'm dead with the name, so we can keep track of which object was actually deleted. And then otherwise, I'm just creating P1, and then I'm going to do a get refers on it as well. So watch what happens when I run this program. We get, once again, the globals. Okay, so we've got our list of refers to P1, and the only one referring to it right now is the globals dictionary. Fine. And after that, after we see that P1 is in globals, then this is printed. I'm dead, name 1. Did you kill it? Did I kill it? What's going on? Basically, so long as there is at least one reference to an object, it remains alive. And that reference can be from a variable, and it can be from another data structure. And when the reference count goes away, when it becomes 0, Python deletes the object, releases the memory. We've said that already. But when a program exits, all the variables are deleted. And because the variables are deleted, the references are deleted, and thus all objects go away. So that's why we were seeing the I'm dead message there from P1, because at the end of the program, the global variables were deleted, and thus P1 was deleted, and thus the object was freed up. Let's take a look at a variation on this. So I've still got my class person, but now what I'm going to do is I'm going to create a bunch of people, each with different names, and I'm going to add them into the all people list. So all people is a global list, and I'm just going to say for I in range 3, add person 0, person 1, and person 2. And then after that, I'm going to say, after the loop, ending the program. So what is going to be printed and when? Well, let's take a look. When we run this program, so it's going to say before loop, and then it's going to say after loop, now ending the program, right? That's the last line of our program. And yet after we do that, then we get the I'm dead. So that shows exactly what I was talking about just now, meaning when our program exits, the variables are deleted. Because the variables are deleted, the reference count goes to 0. Because the reference count goes to 0, then the object is freed. And just before that happens, dunder-del is executed. So because all people is a global variable, it's only released when the program exits. Before that happens, it's not actually going to be released, which means if you don't clear out things in your global list, such as here in all people, you are going to have a memory leak. That's right. You're going to have a memory leak in your program. Over time, your program is going to use more and more and more memory as you have, in our particular case, more and more people that are stored there. Now, sometimes there's no getting around it. Sometimes you just have to use more and more memory in your program. That's just the nature of it. But sometimes it happens because you don't pay attention, because you think that, well, it's a garbage collected language, so over time, everything's going to be released, right? Well, not necessarily, only if there are no references to it. And so over time, you can have this growing amount of memory and objects, not objects that you're using or that you care about, but objects that you thought you were done with and yet are available via a global variable and thus are not released. What would happen if I put millions of objects in all people and forgot to remove them when our program was running? And I know you might be thinking, no, what Python is garbage collected, can't have memory leaks. That's what I thought for a long time too. That memory leak is something for C programmers and we can't have them in Python. But you can have them. They just happen in a slightly different way. So how can we get around that? Well, one option is to have local variables, because local variables go away when a function exits, right? So if I put my code inside of a function, then this wouldn't happen, because when we would return from the function, the all people list would have been deleted. The variable name would have been deleted. There would be 0 references to the list itself. The list would have been deleted, and so would all of the objects, then having only the reference from that list. And that's exactly what I can do here. So what I'm doing is I create my class person, and then I have a function, create some people, and the all people list is inside of there. And that local variable is going to go away when the function returns. So I don't have the memory leak here, because every time I run the function, I'm going to create some people, the function returns, and what happens? That's right. I run the function, create 3 people, and then all 3 of them, well, all 3 people are killed. Okay, all 3 of the person objects are removed because there are 0 references, because the function returned. So that's a simple way to get around having memory leaks if you can. But the purpose of this talk is to talk to you about weak references, and that is another solution to this. And a weak reference allows us to refer to an object, but it doesn't add to the reference count, meaning that this additional reference won't stand in the way of the object being removed. Let's take a look at how that could work. So I'm once again going to have my class person, but this time I'm going to use weakref, the weakref module that comes with Python's standard library. And so instead of creating a person object and appending that to the list, I'm going to create a weak reference to the object, which means that if we are the only thing standing between that object getting garbage collected and not, then we're not going to stop it. Our reference does not add to that reference count, and thus it can go away without us. So watch what happens now when I run this program. So all people is a global variable. We're printing before the loop. We're creating 3 people, and then we're saying after the loop. And watch this, before the loop. And right away, time after time after time, the object is going away before the program exits, because the last line of the program here says after loop now ending the program. And this is because I didn't have any other references to any of these objects. So how can I work with weakrefs? Well, I can work with them as per usual, right? I can create a weakref to an object, and then, right, I just say weakref.ref, and that returns a weak reference object. When I want to use that value, when I want to refer to P1 via my weak reference, I actually have to call the weak reference. It's kind of weird, I think, but we invoke it with parentheses as if it were a callable. I mean, I guess it is a callable, right? And so we invoke it and we get that reference back. And then we can say P2 parentheses dot name is the same as saying P1 dot name. Now, what happens when the target object dies? What happens if I have a weak reference to P1 and then I kill off P1? Well, watch what happens here. We say del of P1, remove that strong reference. Now P2, our weak reference, it knows that P1, the variable, was the last reference to it. So there is no more object to refer to, and now actually it's none. So P2 will actually return true. Well, it'll return true if we say print P2 is none. By the way, what happens if I still insist on saying P2 parentheses dot name? That is going to actually blow up. I'm going to get an error because it's going to say, wait a second, this resolves to none, and none certainly does not have a name attribute. There is another way to do this, and that other way is to say weakref.proxy. And proxy basically lets us say, you know what, this whole parentheses business is kind of silly. I don't actually want to have to invoke my weak reference to get what it's referring to. Rather, I just want to treat it just like a regular object, and that's what I can do here. If I use weakref.proxy on P1, then I can just say P2.name. No parentheses are needed at all, and it works great. Well, what happens when I delete P1 now? Same thing as before, just about. If I say, what's the type of P2? We now have a weak proxy object, right? So it's no longer going to be none. And so what happens if I say print P2, actually trying to access that value through the weak proxy will now raise a reference error. So this is a different kind of problem. With a regular weakref, it resolves to none. Well, when you call it, it resolves to none if the referent has gone away. In the case of a weakref proxy, it raises this reference error. Now, you can also do something known as a callback with a weak reference. You can say, whenever this object is deleted, I want to invoke such and such a function. And the function gets the weakref object as an argument. But it's already disappeared, so you can't really use it for anything. You can just say maybe what the ID of the weakref object is. I'm not sure why you would necessarily want to do that. So here's a simple example of how to use a callback. So I'm going to say here's a function, right? Def value gone. It's going to print boohoo, the weakref, and it prints the ID is refless. Okay, so this is going to happen when, well, I create my weakref proxy here, and I'm going to pass it 2 arguments. Argument number 1 is the object to which I want to refer. Argument number 2 is this callback function is value gone that I want to have invoked. And now what's going to happen? Well, I'm going to run my program, and it's going to say, before deleting P2 name equals P1, so far so good. We now delete P1, so P2 is the only reference to it, but of course, it's a proxy. So we're going to see I'm dead. Why? Because the object was, died. And then right away, we're going to get the callback to run as well. And only after that do we see done deleting, which is what we wanted to print. So this is from dunder del, and this is from the callback. So where should you actually use weak references? How can they be useful in your day-to-day work? First of all, I should add, weak references, as I've shown them to you so far, many people would say that you shouldn't use them in this way because they're very low level, and I will show you a higher level use as well. But that doesn't mean you should never use them. It means you should think about it. So one great example is in the observer design pattern. So in observers, what we have is one or more objects saying, I'm interested in a central object, right? They're sort of like signing up. They're saying, tell me when something in the state changes there. So you can imagine, for example, having a store object with its inventory. And when the inventory changes, then the accounting system should know. So the accounting system can be an observer of the store, say, let me know when something changes in there, and then I can, change the books around as necessary. Well, that's great. And the way that we would typically implement an observer is to have like a list of observers. Then we can just iterate over each of them and send them a message saying, hey, something has changed here. You should know about that. Well, where do weak references have to do this? Well, the thing is, if you have these observers stored in a list, then that list is holding onto a reference to each of the observing objects. And as the observing objects go away, but the observing list still refers to them, then why are they still around? It's just for nothing. So the weak reference, if we were to use a weak reference in our observers, that ensures that we are not the last thing standing between these objects being freed and not. Let's see an example of how we can implement such a thing. So here I'm going to import weakref. I'm going to define my class person. And my class person here is not only going to have a name, it's going to have observers. Observers is a list. This is going to be the list of observers we want to keep track of. And then we're going to have a method here called add observers. And what we're going to do is get, splat args. We're going to get a whole bunch of arguments, as many as the user wants to pass to us in a tuple of args. And we're going to iterate over that. And we're not going to add each of the objects to our observer. Rather, we're going to add a weakref to that object in our observer. And then, our class can then have an inform observers method, meaning that whenever we want to sort of update observers on our state, we just iterate for each of the observers and send them a message. But notice I have to check that the observer is none, because if it's none, then I know that it's gone away. You could even argue, by the way, that in my inform method here, I should check, it's none, I should get rid of it from the list of observers, but I didn't want to complicate things too much. So I'm going to go through each observer. If I get none back when I invoke it, then I know that, it's gone away. I shouldn't send it a message. But otherwise, sure, I should send it a message. And if I invoke this here, right, so I can say P1 equals person main, and then P2, P3, and P4 are also people. And I'm going to add observers. I'm going to say that P2, 3, and 4, these are 3 people who are going to observe person 1. I guess they're like paparazzi or something. All right. And then if I say P1 inform observers, hello. So what this does is it's going to send that message to each of the people. It's going to say, P2, hello, P3, hello, P4, hello. So far, so good. But what happens then when I delete P2? Right. So I'm deleting P2. That is a variable that's referring to the person object named 2. It's the only reference to that object. Wait, isn't there another reference? Well, it's a weak reference from our observer. So if I used a regular reference, if I used just sort of inserted P2 into the list of observers, then we would have 2 references to that object. But because I used a weak reference, this is the only one. P2 goes away. And when I now say inform observers hello again, P2 is ignored because its weak reference returns none. Whereas here, we're going to get hello again for both P3 and P4. Another use for weakrefs is in caching. That if I want to keep track of a whole bunch of objects, but I don't want my cache to be the thing stopping those objects from being freed, well, I can use that cache, I can do that in caching. I can use a weak reference. And if the object goes away, that's fine. I'll notice that in my cache, and it's not going to do anything bad to me. I do need to check, of course, to make sure that the object has actually gone away. And for these purposes, you might want to use something that's of higher level than the plain old weakref that we've been looking at so far. Because in the weakref module, we actually have 3 classes that can be super useful. We have the weak key dictionary, in which the keys are weakrefs. We have the weak value dictionary, in which the values are weakrefs. And we even have a weak set. And the weak set, of course, allows us to have a set. But if the object goes away, that's fine. We are not going to be the last thing stopping it from going away. Let me give you an example of where we could use weak key ref. or weak key dictionary. And this is in descriptors. And descriptors are a little arcane and a little hard to understand, but I hope that you'll get it from here. And descriptors are actually very common. In fact, methods are defined using descriptors. So understanding the descriptor protocol is actually a good place to understand Python more deeply. This is not a talk about descriptors, so I hope you'll at least get the flavor of what's going on. And a descriptor is a class attribute. So, and if it's an attribute, then it must have an object, and everything's an object. But the attributes class, the attribute that we define, the class defines two methods, one of both methods, dunderGet and or dunderSet. If I try to retrieve the value of that descriptor, of that class attribute via the instance, and remember, attributes on a class are available via the instance. So if I retrieve the descriptor attribute via the instance, it invokes the dunderGet method. Notice, I'm just retrieving, I'm not invoking, I'm not using parentheses, but dunderGet will still be invoked. And if I try to assign to the descriptor, then dunderSet is invoked. Now, how is this relevant? Well, because a descriptor is a class attribute, there's only one for all the instances of that class. But if we want to have separate values for each of the instances, then we're sort of stuck, right? So we could use a dictionary, and that's a really common thing to do. If we use a dictionary to keep track of our descriptor values, then that works perfectly. We use the instance of our class as the key, and the value that we want to keep track of as the value. Problem solved. But what if the instance goes away? Then we're stuck. Then we are once again holding on to a reference, and we're the only thing stopping that object from going away. Let me give you a more concrete example here. So let's assume we want to have an age in a person, right? So I want to have people, I want to be able to keep track of their ages. I could use an integer, but I want to make sure that the age is not less than 0, not greater than 120. I want to have some boundaries on that age. So I'm going to define an age class, and that's going to be set to be a descriptor on my person class. So my person class, def init self-name equals name, just like before. And now I say at the class level, age equals age. So age, lowercase age, a class attribute, and it is an instance of the age class. Now what are we going to do? Well, this is the implementation of my age class. First of all, it's dunder init. And what do we do in dunder init? We're going to keep track of all the ages of all the people in our weak key dictionary. And whenever someone asks for the age from a person, this method, dunderGet, is going to be invoked. And what are we going to do? Well, we're going to get the instance. That comes naturally and automatically through the descriptor protocol. And then we just go to self.ages and pull out the age for that instance. And when we want to set, well, we can have some checks in here for not less than 0, not greater than 120. But otherwise, we're going to assign into self.ages with the square brackets of instance equals new age. And so this works really well. Moreover, this is how you should do descriptors, because if one of the person objects goes away, we don't want it to be stuck in memory and effectively create a memory leak just because we're holding on to its age. Okay, let's summarize. Weak references provide us with a lot of insights into how Python does garbage collection and freeing of memory. And it's hard, not impossible, but hard to leak memory in Python if you're not careful, especially if you're using global variables. And the key thing to understand is you might end up keeping objects around much longer than you want or than you expect, thus causing memory in your program to grow and grow and grow over time. And so weak references can allow you to ensure that your data structures and these variables and the way you're storing them are not the reasons objects are sticking around. I hope this was useful and helpful. If you have questions or comments, please contact me. I'm always open to hear from people. You're also welcome to join 20,000 other Python developers who receive my weekly Better Developers free weekly newsletter. And I look forward to being in person at PyCon Israel in 2022. Thanks again.